Let's review the connections we've made so far between electricity and magnetism. Electric charge comes in two varieties, positive and negative. With magnetic fields, we have a north pole and a south pole. In both instances, likes repel, opposites attract. Electric charges that are moving and currents feel a force from a magnetic field. And finally, electric currents can produce magnetic fields. Wouldn't it all be nice and symmetric if magnetic fields could produce electric currents? Turns out that our universe is quite symmetric. Michael Faraday discovered in fact that you could produce electric currents from magnetic fields. The general idea that he came up with was if you take a bar magnet and move it next to a coil of wire, you could in fact make a current flow. But if the bar magnet was sitting still, there was no current flowing. So what's going on here? We need to investigate a new quantity that we call magnetic flux. Magnetic flux is telling us the number of magnetic field lines that are going through a loop of wire. The number of magnetic field lines, as you can see in the diagram here, might depend upon the number of field lines that the magnetic field has, the strength of the magnetic field. Another thing it might depend upon is the area of the loop. A large area can fit a lot of magnetic field lines in, a smaller area can fit fewer. The other thing it might depend upon is the angle made between those magnetic field lines and the loop, and we'll call that angle here theta. So our magnetic flux, which we'll use the symbol capital letter phi, the Greek letter here, we can write as depending upon all of those factors, it will be the magnetic field strength, B, multiplied by the area of the coil, A, multiplied by the cosine of the angle, cosine theta. So there's a measure of how many field lines are going through the loop. What Michael Faraday discovered was you get an induced EMF, a voltage that will drive a current, if you change that magnetic flux. And in particular, that induced EMF depends upon the rate of change of the magnetic flux. So we can write the change in magnetic flux, delta phi, divided by the change in time, the rate of change of magnetic flux. And for the time being, I'll put a little minus sign out the front here, which we'll talk about a bit more in a minute. That's going to tell us something about the direction that that EMF drives the current. So if we go back and look at our example now of the magnetic field pointing into the coil as we move the magnet, we'll see how this changing magnetic flux works. In the top of the diagram, our magnet isn't very close to the coil yet, and the magnetic field lines coming out from the North Pole, some of them will go through the coil, but others will miss the coil. So there's a fairly small magnetic flux through the coil. As the magnet gets closer to the coil, more and more of those magnetic field lines will point through the coil. The magnetic flux is increasing as we take our magnet closer and closer to the coil. That's why as the magnet was moved into the coil, the increasing magnetic flux caused an induced EMF that drove the electric current in the coil. Now there's a couple of options here. Which direction does that electric current flow? It could flow clockwise or counterclockwise depending how you looked at it. An interesting point to note here is that electric current that's flowing, as we've seen in the last topic, it will produce its own magnetic field, which will have a north pole pointing one way and a south pole pointing the other. It would be kind of nice if the magnetic field from the induced current was one that would attract the north pole end of the magnet into the coil. That would mean if we just pushed the magnet a little bit towards the coil, that would change the magnetic flux, that would induce an EMF that would drive a current that itself would have a magnetic field that would pull the magnet further in, which would also change the flux, and so on and so on. That means we could just nudge the magnet and it would just fly into the coil, producing an electric current the whole time. Unfortunately, our universe doesn't work that way. In our universe, as we put the magnet closer to the coil, the current that's induced has a magnetic field that opposes the change in magnetic flux that was first there. That's what we call Lenz's law, and that's what the minus sign that we wrote before is there to remind us about. The induced EMF opposes the change in flux that caused it in the first place. That means as we're pushing the magnet in, the current that flows in the coil will produce a magnetic field that tries to push the magnet out. And in the opposite sense, if we were pulling the magnet out of the loop, which is of course another way of changing the flux, then a different direction current will flow to create a magnetic field that tries to pull the magnet back in. Whatever direction you're changing the flux creates a current that opposes that change in flux. And again, we call that Lenz's law. Now, here's an example of how we might change the magnetic flux, not by pushing a magnet in or out, but by making the coil change its angle. You can see here that in fact, if I have my magnetic field lines coming out through my coil, because it's at an angle, I get fewer of them through than if it wasn't at an angle. What if I change the orientation of that coil? If I was to spin that coil, I would get fewer and fewer as the coil got flatter and flatter to the magnet. As the coil became more at right angles, then I'd get more and more through. I could sit there and rotate the coil in the magnetic field, and indeed I'd be driving a current continuously through the coil. That sounds like a good idea, a way of generating a current. In fact, rotating a coil in a magnetic field is what we call a generator. You could hook up the coil to anything you had handy, maybe some kind of petrol engine, maybe a hamster and a wheel, and it could spin that coil for you all the time, generating electricity. In fact, if you go to a large electric power plant, you'll find them burning coal or running hydroelectric water through a turbine to do just that. They're simply spinning coils in magnetic fields. So that finishes our module on electricity and magnetism. We've covered a lot of territory, from a simple understanding of electric charge, the forces between them, moving charges causing currents, looking at currents in circuits involving voltages and resistances, and then moving on to magnetic fields, magnetic forces, and finally the interaction between electricity and magnetism. In Module 4, we're going to move on to examine light and optics. We'll be looking at a range of phenomena, including the wave properties of light, image formation using mirrors and lenses, and fibre optics and lasers. So I'll be seeing you then.